Today, I want to talk about what it means for a set of random variables or a set of events to be independent of one another. As always, let's start with a story. Bounty hunters were following the pirate captain's ship. There were 5 different bounty hunters, each working independently. If each bounty hunter had only a 20% chance of catching the captain's ship, then what was the chance that at least one of the bounty hunters caught up? Now, sometimes information about whether or not an event like Q is true does not give us any information about whether or not event P is true. In that case, call the 2 events independent. Note that if the probability of P given Q equals the probability of P, not knowing whether Q is true, then the probability of P equals the probability of both P and Q divided by the probability of Q, which means the probability of P times the probability of Q equals the probability of both P and Q. In general, events P and Q are independent if the probability of both P and Q equals the probability of P times the probability of Q. This is a perfectly symmetric definition. If P and Q are independent, then so are Q and P. P and Q are independent, then the probability of Q and P equals the probability of P and Q, which is the probability of P times the probability of Q, which is exactly the probability of Q times the probability of P. Another way to talk about independence is in terms of conditional probability. Suppose that P and Q are events with the probability of Q greater than 0. Then P and Q are independent if and only if the probability of P given Q equals the probability of P. If P and Q are independent, it means that knowledge of the one has no effect on knowledge of the other. Therefore, it stands to reason that P and not Q should also be independent, because knowing if Q is not true should also not affect P. If P and Q are independent, then so are P and not Q. Proof goes as follows. Suppose that P and Q are independent. Then PQ and P not Q form a disjoint partition of P. So the probability of P is the probability of PQ plus the probability of P and not Q. Rearranging gives that the probability of P and not Q is the probability of P minus the probability of PQ. Now use the fact that P and Q are independent to say that that equals the probability of P minus the probability of P times the probability of Q. We can factor out the probability of P. What's left is a factor of 1 minus the probability of Q, but that's just the probability of not Q. So we've shown that the probability of P and not Q is the product of the probability of P and the probability of not Q, which means that P and not Q are also independent. So what should it mean for events S1, S2, up to Sn to be independent? What should the independent of a sequence S1, S2, etc. mean? The idea is to consider all finite subsets of the set of events. A finite set of events, S1 up through Sn, are independent if for all I, a subset of 1 up through n, the probability that every Si with little I in big I holds is equal to the product over little I in big I of the probability that event I holds. This always holds when I has no events or just one event, but it must also hold when I contains 2 or more events. So the number of requirements grows quickly in n. For n equals 3 and events S sub 1, S sub 2, and S sub 3, this requires that the probability of S1 and S2 be the probability of S1 times the probability of S2. The probability of S1 and S3 equal the probability of S1 times the probability of S3. The probability of S2 and S3 equal the probability of S2 times the probability of S3. And the probability of S1, S2, and S3 to equal the probability of S1 times the probability of S2 times the probability of S3. Note that it is possible for the last equation to be satisfied, but not have one of the first 3 hold true. When n equals 4, there are 11 such equations, and when n equals 5, there are 26. So usually independence works in the reverse direction. Rather than using the equations to prove independence, independence is assumed, and then the equations can be used to break any logical and into multiplied probabilities. Now, disjoint events allow probabilities of logical OR to be turned into sum. Independent events allow probabilities of logical AND to be turned into product. They should not be confused. In particular, disjoint events with probabilities strictly between 0 and 1 mean that at most one of the events can occur, so they are never independent. A similar result as before holds for negations. If S sub 1 through S sub n are independent events, then so are F sub 1 through F sub n, where for each F sub I, either F sub I is S sub I, or F sub I is the negation of S sub I. The proof uses induction on M, the number of I, such that S sub I equals the negation of S sub I. So how should the independence of an infinite sequence of events be handled? A sequence S sub 1, S sub 2, etc. of events is independent if for every n in 1, 2, 3, and so on, the events S sub 1 up through S sub n are independent. Again, it's actually pretty rare to have to prove directly that a sequence is independent. Instead, it is often something assumed based on the situation, and then the property can be used. So let's solve the story. Back to the pirate and the bounty hunters. Let S sub I denote the event that the ith bounty hunter catches the pirate captain. Then the captain is interested in the probability that at least one of the bounty hunters catches the ship. That is, the goal is to find the probability of the logical OR as I goes from 1 to 5 of S sub I. Now, the problem implies that the S sub I are independent, but independence inside probabilities only applies to a logical AND. The problem, the goal that we're looking for, uses logical OR. The solution is to use De Morgan's laws to switch from AND to OR. Recall that De Morgan's laws state that the negation of the logical OR as I goes from 1 to 5 of S sub I equals the logical AND as I goes from 1 to 5 of the negation of S sub I. So the logical OR of the S sub I is the negation of the logical AND of the negation of the S sub I. Applied to our captain's question, the probability of the logical OR of the S sub I is the probability of the negation of the logical AND of the negation of the S sub I, and that is equal to 1 minus the product of the probabilities of the negation of the S sub I. Each S sub I has probability 0.2, so the negation has probability 1 minus 0.2, or 0.8. Each of them is the same, so multiplying it by itself 5 times is the same as raising it to the 5th power, and 1 minus the quantity 1 minus 0.2 to the 5th power is 0.67232. So our bounty hunters have about a 67.23% chance of catching the pirate captain. Now let's look at an example where the probability of S1 and S2 and S3 equals the probability of S1 times the probability of S2 times the probability of S3, but all 3 events are not independent. The example uses X, a D27, so it's a roll of a fair 27-sided die. Suppose S sub 1 is the event that X is at most 18, S2 is the event that X is at least 10, and S3 is the event that X is at least 11, or X equals 1. Then the probabilities of S sub 1, S sub 2, and S sub 3 are all 18/27, or 2/3. And the probability that all 3 occur, S1 and S2 and S3, is the same as the probability that X is in the event from 11 up to 18, which is 8 out of 27. Now this is 2/3 cubed, and so that just equals the probability of S1 times the probability of S2 times the probability of S3. So are those independent? Well, no. And there are many reasons why. One is that the events S sub 1 and S sub 2 are not independent. The probability that both X is at most 18 and X is at least 10 is 9/27, while the probability that X is at most 18 times the probability that X is at least 10 is 2/3 times 2/3, which is 4/9, which is 12/27. So even though the logical and of the three events can be broken up into the product of the probabilities of the three events, that's not enough to say that all three of the events are independent. Now, the notion of independence can also be extended to random variables. We say that random variables X and Y are independent if for every pair of measurable sets A and B, the probability that X is in A and Y is in B equals the probability that X is in A times the probability that Y is in B. In other words, random variables are independent if and only if every event involving the random variables is independent. As with sequences of events, usually it is assumed that random variables are independent so that the rules can be applied. So that's what it means for random variables to be independent of one another. The probability that both things happen is the product of the probabilities that the individual things happen. See you next time.